Now I talked a little bit about taking derivatives of hyperbolic trig functions. And of course we can do that, but we can also integrate them. For instance, if we have hyperbolic trig, let's say we have cosh of 4x dx. And we look at that, we want to integrate that. Well, this is just like we've done previously. We say, I want to know, what I really wish it says is just cosh of u, because if it said cosh of u, the integral would be sinh of u. And so, I make my substitution, u equals 4x, du dx equals 4. Rearranging that, I get dx equals du over 4. So, okay, I'm going to make that substitution in here. This becomes cosh of u. Dx becomes du over 4. And I end up 1/4. And then it's cosh u du, which integrates precisely to sinh of u. And then we say, well, we really want to be back in the x world, so that's a 4x in there. Right. Similarly, all the various things that we do with trig functions, we can do with these hyperbolic trig functions. If we have something like sec squared, well, that means it's going to integrate to tangent. If we have something like, cotangent, cosec, or cotang, cosec, then it's going to integrate to negative cosec, etc. So we can follow those kinds of things. In addition, with the 7 formulas that I just put up there a minute ago, we have 7 analogous integrals that we can solve. For the inverse hyperbolics, those look like this. There's a little bit of difference in what I did with the derivatives and what I did with the integrals, because of the fact that different things other than just one can be in those denominators. So the integral, when you see something of this form, or notice the a does not have to be 1. We already looked at the case where the a was 1. But that result is an inverse sinh of u over a. And then, of course, plus c. Similarly, if we had this 1 over u squared minus a squared, it's going to be an inverse cosh of u over a plus c. If we had 1 over u times a squared minus u squared, then that will give me an inverse sec of u over a. And in that case, we have an additional term out front, which is a 1 over a, minus 1 over a. So it matters that whether this is a 1 or not. It shows up both here and here. For inverse sinh and inverse cosh, it only shows up inside the argument. And of course, we've got plus c here. And 1 over a squared minus u squared du integrates to the inverse tang of u over a. And again, with that one, we get a 1 over a out front. So when that's not a 1, all the derivatives I showed you, that was a 1 that we got as a result of taking a derivative. When it's not a 1, what ends up happening is it just shows up as a 1 over a inside and then sometimes on the outside as well. Of course, we already had the ones with the inverse regular trig functions, which were somewhat similar to that. If I can copy them up real quick here. They looked like this. We had integral 1 over square root a squared minus u squared, which is kind of the opposite of that one. And that gave us inverse sine of u over a plus c. We had 1 over a squared plus u squared. And that gave us inverse tangent of u over a plus c, and then there's a 1 over a in that case. And the square root of u squared minus a squared. And that gave us a 1 over a and an inverse secant plus c. So those are the 7 forms that we can look for that we've generated by taking these derivatives not only of inverse sine functions, but also of inverse hyperbolic sine, or trig function, inverse trig functions and inverse hyperbolic trig functions. Allows us 7 more forms that we can look for when we're trying to solve a problem and integrate it.